KIM-1 single-board computer was released to the market in April 1976 by MOS Technology, Inc. out of Norristown, Pennsylvania in the United States. MOS Technology had created the 6502 CPU, and the KIM-1 computer was a way to get their CPU in people's hands and show what it was capable of. The KIM-1 was no doubt a complete computer system. It had the 6502 CPU at its heart. It had two MOS 6530 chips, which provided I/O, timing, the kernel ROM to the extent that you could call it a kernel, and a small amount of RAM on each 6530. The KIM-1 also had 1K of onboard RAM. That's enough for me to classify it as a complete computer system, and it was comparable to other systems at that time. But the KIM-1 was limited in several ways. It did not natively have a video display. The default output device was these 6 LEDs. The input device was a tiny calculator keypad, and for external storage, the options natively available to the KIM-1 were audio cassette or paper tape. MOS did not provide any disk storage options for the KIM-1. In fall 1976, a few months after MOS Technology released the KIM-1, Commodore International purchased MOS Technology as part of a vertical integration strategy. At the time, Commodore was primarily a calculator company, and they sought to have an in-house chip fab to make their own calculator chips. Commodore continued selling the MOS KIM-1, although they changed the branding on the board to include Commodore's name along with the original MOS moniker. The corporate marriage of MOS and Commodore is what gave birth to the Commodore PET computer in 1977. The PET was obviously built on the same concepts as the KIM-1, but it addressed some of the KIM-1's limitations. It was a 6502-based computer with dedicated MOS chips to provide I/O and timer functions. The keyboard was improved over the KIM-1, but still resembled a calculator more than the computer keyboards we've become accustomed to today. External storage still utilized audio cassettes, but the PET came with an integrated cassette drive. If you're only going by appearance, it's easy to look at a PET and a KIM-1 side by side and not think of them as similar computers, but they really weren't all that different. Be that as it may, when Commodore began to release disk storage devices in late 1978, they were IEEE 488 devices for use with the PET. Commodore made no attempt to create an interface to allow their KIM-1 computer to utilize their new line of IEEE 488 disk drives. When Commodore turned their attention to the low-cost consumer market with the release of the VIC-20 computer in 1980, one of the cost-cutting measures was to eliminate the IEEE 488 bus, mainly because of the cost of the physical connectors. So the VIC-20 and the Commodore 64 after it utilized the Commodore proprietary IEC bus that was native to their new 1540 disk drive and subsequently the 1541 disk drive that was released in 1982. By this time, the KIM-1 was basically a dead platform. Commodore made no attempt to make their IEEE 488 drives compatible with the KIM-1, and they certainly had no incentive to make their new low-cost IEC drives compatible with the KIM-1. And that brings us to the entire point of this video. We know Commodore never did it, but is it actually possible to do? Can we hook a 1541 disk drive up to a KIM-1 single-board computer? Let's find out. I established that Commodore never produced a disk drive for the KIM-1, but other companies certainly did. The May 1980 issue of Byte magazine shows one such example. On page 44, you can read about interfacing the PERCOM LFD 400 disk system with the KIM-1. PERCOM ported their own mini-DOS disk operating system to the KIM-1 and renamed it KIM-DOS. In the case of the PERCOM device, KIM-DOS ran on the KIM-1 and had to know everything about the disk drive, including how data was organized on the disk. So, we know it's possible to hook a disk drive up to a KIM-1. Now, what's next? Well, there are really two things we have to figure out: the hardware side of it and the software side of it. The hardware side is the actual electrical connectivity, how we connect the KIM-1 to the IEC bus that connects to the 1541 disk drive. The software side of it is writing the code so that the KIM-1 knows how to tell the 1541 to load and save files. So we'll get started with the hardware side first. Let's go look at a schematic for the C64 and see how that connects to the IEC bus. Here's a Commodore 64 schematic I grabbed from Zimmers.net. As I mentioned earlier, all of Commodore's 8-bit consumer computers were IEC compatible, so I could have looked at any of their schematics. The C64 is familiar to most folks, so I chose to use it as an example. There's no other reason. Let's start over here on the bottom left. The 6-pin serial bus shown here is the IEC bus connector on the C64. I'll walk through the pins starting on the left with reset. Reset goes up off the screen there somewhere, and we don't need to care where it goes on the C64. The KIM-1 provides a reset signal on its expansion connector, so I'm going to use that. Pin 1 is the SRQ or service request line. I'm not going to worry about this either because it's not used. You'll just have to trust me on that one. Pin 5 is the data line. That connects to pin 9 of the U2 6526 CIA. That's the PA7 pin. You can see it goes through FB8. Ferrite beads are used to suppress high-frequency noise. We can probably live without these, so I'm not going to include them on my breadboard. While I'm over here, though, I see that data out on PA5 connects to the same IEC line. That's going through U8, which is a 7406 inverter. Duly noted, I'll need a 7406 on my breadboard. Back to the IEC connector on the bottom left and moving on to pin 4, the clock line. That connects to PA6 of the CIA. Same deal as with data. PA4 coming out of pin 6 of the CIA as the clock output connects to the same IEC clock line, and that also goes through the same U8 7406. Staying with the CIA for a moment, I see that the IEC attention line is output from the PA3 pin of the CIA. That connects over to the IEC connector at pin 3. Before I move on, I want to point out that the clock, data, and attention lines each require a 1K pull-up resistor. I'll need to remember to put those on my breadboard. The last IEC line I'll need to deal with is pin 2 over at the IEC connector, which is a ground. That's easy enough. This doesn't look too bad, really. There's very little involved here. However, let's talk about the elephant in the room. Look at all the lines over here connected to the 6526 CIA chip. A KIM-1 doesn't have a 6526 CIA chip. So are things about to get a whole lot more complicated? Not necessarily. There was purpose to my earlier mention of how fundamentally similar the KIM-1 and PET computers were. In fact, all of Commodore's 8-bit line were fundamentally similar. They all have some variant of a 6502 CPU, some memory, and some variant of I/O/timer chips. The C64 used 6526 CIA or complex interface adapter chips for I/O and timers. The VIC-20 used 6522 VIAs or versatile interface adapters. The PET used 6520 PIA or peripheral interface adapters, and it used 6522 VIAs. The KIM-1 used 6530 Riot chips. Let's take a look at the 6526 and 6530 datasheets. The 6526 is on the left, and the 6530 is on the right. For the purpose of hardware connectivity, I only care about the pinout right now, so let's focus on that. Here's that mess of lines connected to the 6526 at U2. Data on PA7, clock on PA6, data out on PA5, clock out on PA4, and attention out on PA3. And here they are shown on the 6526 pinout. So what are PA3 through PA7? Well, they're the I/O lines. The 6526 has 16 total, PA0 through PA7 and PB0 through PB7. Each of these pins can be programmed as an input or an output. They're how the computer connects with the outside world. And what do you know? The MOS 6530 has PA3 through PA7 pins also. They serve the exact same purpose as the peripheral I/O pins on the 6526. From a hardware perspective, this should all just work. I should be able to use the KIM-1's onboard 6530 to communicate on the IEC bus. What you're looking at here is basically the schematic I'll be using to interface the KIM-1 to an IEC bus. On the KIM-1, the 6530-003's I/O pins are all exposed on the KIM-1's application connector. So all I need to do is build a simple breadboard with a 7406 and an IEC connector on it. I'll connect PA3 through PA7 from the KIM-1's application connector to inputs on the 7406, and I'll connect the outputs of the 7406 to the IEC connector. I need a way to connect the IEC lines from a breadboard to a 1541 drive. There are probably 100 better ways to accomplish this, but I'm using what I happen to have on hand. These male DIN connectors will go to the back of the 1541. The 6-conductor wire will connect to that, and then I'll solder the other ends of the wire to a socket, which I'll insert into my breadboard. The breadboard that's already connected up at the top there is an 8K EPROM expansion board. Once I get to the software part of this video, you'll see that that's where my load and save routines for the 1541 will be stored. If you want to know how that works, I did an entire video about how address decoding works on the KIM-1, which shows how I built that expansion board. My first step here is going to be to get power and ground over to the new board. I'll attach my homemade breadboard socket to IEC cable. Now I can install the 7406 on the board. PA3, PA4, and PA5 connect from the KIM-1's application connector to inputs on the 7406 inverter, then from the outputs of the 7406 to the IEC lines. The IEC reset line just connects straight up to the reset line that's exposed at pin 7 of the KIM-1's expansion connector. These are the last two lines I need to connect, clock and data from PA6 and PA7 of the application connector, and they go straight to the clock and data IEC lines without passing through the 7406 inverter. Pull up resistors, and I am done with the hardware part of things. I'll do a quick test here. Without having software that knows how to talk to the drive, I can at least make sure there's no smoke when I power things on. I can also test that pressing reset on the KIM-1 will cause the 1541 to reset. I'm about as done with the hardware side of things as I can get for now. It's time to turn my attention to the software side of things. I need code that will run on the KIM-1 and knows how to talk Commodore's IEC bus protocol. Where to even start? Well, that intro I did at the beginning of the video, that wasn't just filler material. I really wanted to convey just how similar all of Commodore's 8-bit machines are. I mean, we know we already looked at the Commodore 64 schematic and stole the hardware implementation for the IEC bus connectivity. There's nothing stopping us from stealing the serial routines from the Commodore 64 kernel. Let's go take a look at that now. What you're looking at here is the disassembled C64 kernel source code. There are quite a few places on the internet where you can grab this these days. I chose this source because I'm a fan of Michael Steele's work. It's always thorough and detailed, so I tend to trust things I find on his site and not spend time verifying. Anyway, the URLs are listed here for you if you want to check it out yourself. This is a disassembly that was provided by Commodore. You can see it contains the Commodore disclaimer in this comment. When I talk about how similar the Commodore 8-bit machines were, the IEC serial routines in the C64 kernel are another great example. The IEC routines were ported from the parallel IEEE PET routines by Steve Harris, Bob Russell, and Glenn Stark. A quick history tidbit, all three of these fellows were recruited from Iowa State University by John Fagans, who was also an Iowa alum. It was Glenn Stark who developed the prototype 2031 drive from which the 1540 evolved. If you look at the IEC routines in the VIC-20 kernel and the C64 kernel, they're almost a direct copy and paste. I chose to work from the C64 kernel sources only because I'm slightly more familiar with them overall, but you really could grab the source from any of the Commodore kernels that support IEC drives. As we get down here to where the actual code begins, you'll notice that my formatting diverges greatly from the original. I assembled using 64 tasks on Linux, so some of the changes I made were to match 64 task syntax. Some were just to improve readability for myself. Most of what you see here are the original labels from the C64 kernel source, and I tried to keep things at the same memory locations where possible. I only used labels I needed for the serial routines, so if you're comparing this code against the actual C64 kernel, you'll notice a lot missing here. A choice I made when I implemented this was to make the user experience match that of the KIM-1 tape load and save routines. I used the user-provided tape ID as the file name for disk storage. As such, you can use 01 through FE as file names on disk, just like when saving to tape. I also used the same start and end address locations as the tape routines. Other than the disk load and save routines living at different addresses on the KIM-1, you can follow the tape load and save routine instructions from the KIM-1 user manual, and it works the same for disk load and save. LD init is a label I added. It's initialization code for the load routine. A key thing to mention here is where I set up the 6530 data registers labeled PAD and data direction registers labeled PADD. The values I stored there are unchanged from the C64 source. When I did the hardware connections, I intentionally used the exact same peripheral application pin numbers as were used on the C64. Because of that, this code does not need to be changed. The data register and data direction register on the 6526 and 6530 operate the same. Bit 0 represents peripheral pin 0, bit 1 represents peripheral pin 1, and so on. I had to change very little in the C64 kernel load routine. The very first subroutine call there, conv ID, is one I added. The user stores the tape ID as a single byte number from 01 through FE. Conv ID takes that number and converts it to 2 ASCII bytes, which are used as the disk file name. Very minor change I made. This code doesn't support pressing the stop key, so I commented that out. The entire rest of the load routine is effectively unchanged. I really had to change that few things to make this work on a KIM-1. This section here is random glue code I had to write. I couldn't support things like a file not found error being displayed because I wrote to the lowest common denominator, 6 LEDs for output. So I write error codes to the My Status label to be inspected after the code runs. This is the routine that converts the tape ID to ASCII. It's pulled almost directly from the original 6530 ROM. I created SVinit to initialize things for the save routine. This one is mild spaghetti code. I removed the indirect addressing bits to make it less complex, and I also integrated the KIM-1 tape save addresses to make things user-friendly. The result is about a zillion labels, all with similar names being used for similar but not exact things. And again, I commented out the check for stop there. Now I'm down to the serial library routines. This is where the deep voodoo happens. If you watched my prior video that shows how the IEC protocol works using a logic analyzer, this is the code that implements all of what you saw in that video. Because it's a lot of code, and because I had to change very little of it, I'm not going to scroll through the entire thing. I'll just hit a few highlights. Here's one change. The C64 kernel code used an interval timer on the 6526. I just had to convert that to use an interval timer on the 6530. Same exact thing here. This was another 6526 interval timer. I converted it to be a 6530 interval timer. One quick anecdote to close out the source code section of the video is that I've always read how critical the timing of this code is. Indeed, if you look at the source, you'll see a few places where they put a lot of care into wasting a few cycles here or there. It terrified me when I started working on this project. The funny part, however, is that when I was converting over the interval timer code, I initially wrote all of my 6530 code to match what the comments said the code was doing. I later found out that it didn't match what the actual code was doing. That's when I discovered that some parts of the timing aren't very critical at all, but other parts really do matter. I assembled the code using 64 tasks on a Linux machine with an origin address of hex 2000. I'll burn that binary image to a 2764 EPROM that I can install on the KIM-1 expansion board I built in a previous video. Go check that one out if you're curious how that part works. I only implemented load and save so far on the KIM-1, so before I can load or save, I'll need to format a disk somewhere else. I'll walk over to the C64 corner of the Commodore room to handle that. This is it. You finally get to see a KIM-1 single board computer save data to a Commodore 1541 disk drive. Before I do anything else, I'll set up the vectors on the KIM-1. This way things like the break instruction do meaningful stuff. This isn't really related to the disk drive code. This is just something you do every time you boot a KIM-1. I'll go to hex 200 now and enter some data that I can save. I'll just count up from 0 through E. That way it's easy to load back and verify that it worked. Next, it's straight out of the KIM-1 user manual for how you save to tape. Enter the start address at 17F5, low byte first. Enter the end address at 17F7, also low byte first. Then the tape ID at 17F9, which, as you recall, I'm using the tape ID as the file name when I save to disk. I made the user experience identical to saving to tape. The disk save code lives at hex 2148, so here it goes. I don't have a way to load a directory on the KIM-1 yet, so let's walk back over to the Commodore 64 and see what was written out to the disk. We should see a file named 01, and it should contain 0 through E hex. I'll exit out of HESMon for a moment and load the directory. We want to see file 01. There it is. Because the load address is hex 200, I'll load it using HESMon, which will make it easier to view the memory. When I started working on this project, I had no idea if it would work. You can imagine how excited I was the first time I saw this. I confirmed that the save routine's working. Now let's make sure the load routine works. I'll power things back on here and try to load that file back from disk to the KIM-1. I'll speed this up so you don't have to watch me doing this boring initialization stuff every time. Now, to load, again, straight out of the KIM-1 user manual for how you load from tape. The file name goes at 17F9, 01 there, and then we go to the start address of the disk load routine, which is hex 2000, and we go. But first, let's look at hex 200, just to confirm that there's nothing there already except rubbish. Back to 200, and there's the data I saved. It's a beautiful thing to see. Another video done. I don't expect this will get a whole lot of views because I tend to do these topics that really people don't care a whole lot about except me. But I have an awful lot of fun doing them and learning stuff along the way. And if you do happen to watch them, I hope you enjoy them and learn something also. I'll see you next time.